Hello everyone and welcome back to this Nanophotonics and Plasmonics course. So this is the third and final video for chapter 6 on photonic crystals. So this video will focus more on the fabrication, those photonic crystals, and how they can be actually engineered to drive specific applications. So this is just an example of fabrication technique. There are multiple fabrication techniques. We're going to just touch upon a couple of them later on, but this is one which typically involves multi-step lithographic and deposition techniques to fabricate those three-dimensional photonic crystal. So in this particular example, we start with a silicon substrate into which we drill holes. So we etch those circular holes into the silicon substrate to form a triangular lattice. Then we can backfill those holes with silica, polish the upper surface to get a very clean interface, and redeposit an additional layer of silicon. So now the substrate and this layer are both made of silicon. So the idea is to drill another set of holes. So we have a new series of holes which is offset respect to the first one. And also overlapping. So this overlap is in the here very important. So the second series of holes is offset and overlapping respect to the first one. Then we backfill those holes again using silica. We repolish the surface again before adding another layer of silicon and drilling new holes that are also offset and overlapping as well. We can continue all the way up, alternate layers of silicon, drill holes, backfill them with silica, polish, and so on and so forth. And once we reach the number of periods we want, we can just dissolve silica in all the holes at once, and we're left with empty holes inside the silicon matrix. So this is just an example of one period. So you see that we have three set of holes, A, B, and C, that are offset and overlapping respect to each other's. And then we start again with a new set of A, B, C, and you keep going as long as you want. So you see, with this technique, this is extremely time consuming because you have a lot of steps involved between the etching of the holes, backfilling with silica, polishing the surfaces, redepositing, and so on and so forth. That this is extremely time consuming. So if you focus a little bit on what we obtain with the structure, if you take a cross sections along those black regions here, you can see that you're gonna have circular holes organized on the hexagonal or triangular array within those layers made of silicon. If you offset the cross sections a little bit, then you can see that in those other black regions you have more empty space than silicon. So silicon is left with those tiny regions that are forming those simple silicon rods. So you have alternating layers of circular holes in silicon and silicon rods. So this is the resulting photonic crystal you obtain with this particular fabrication technique. So you see that you have those three circular holes that are offset respect to each other's, that are inside those silicon layers. And in between those silicon layers, you have those silicon rods that we just talked about. So this is a SEM image of such a structure. So you see that you can achieve very large scale for those structures, tens of microns in size. This is a close-up view showing those circular holes, successive layers. So you can see the underneath layers with the holes that are offset respect to the first layer. This is a calculated photonic band structure for this particular photonic crystal. So it's a 3D photonic crystal, FCC type of crystal. So you really have a more complex Brilliant zone that we've seen so far, and we have the opening of a very large photonic band gap in this particular case. So you have this large range of frequencies or energies for which the wave will not propagate through the crystal. So this is just one particular example, as I said, with one particular fabrication technique. We can obtain a very large variety of different type of 3D photonic crystals. These are just some examples. So the wood pile is a typical example of photonic crystals, which is just alternating layers of parallel nanowires that are typically composed of silicon, and those successive layers are actually orthogonal with respect to each other's, and you can just stack them up as high as you want. So once again, those things are done using lithography techniques typically. You can have also opals forming those 3D photonic crystals. So this is something which is typically done using chemical synthesis and colloidal solutions of nanoparticles. Once the solution evaporates, then you're left with nanoparticles that are self-assembling into FCC type of lattice. So it's something which is also very easy to fabricate, although you have less control over the periodicity and the presence of defects, but you can achieve extremely large areas. You see that this is 50 micrometers in size, so you see that this whole batch here is a few hundred micrometer in size. The inverse opals, as its name indicates, is the inverse of the opal. So you have a matrix that could be composed of silicon, for instance, and you have circular holes that are left behind when dissolving the materials that compose those spherical particles. And then we have more exotic structures, so the slanted pores or the circular spirals. Those structures that are a bit more recent basically rely on 3D printing techniques. So another thing which is very important in photonic crystals is the presence of defects, which are typically introduced artificially to be able to localize or guide light. So when light with a frequency which is within the photonic band gap cannot propagate through the crystal, but if you have a defect which is present within this crystal, light will be able to either propagate or be confined within the regions of the defects. So I want to show you right now finite difference time domain simulations. They're actually illustrating how light behaves in the presence of defects in photonic crystals. So this is the first example, which is just a reminder of what we've seen. So you have an hexagonal array composed of silicon nanoparticles. And if we send a plane wave with a frequency which is in the photonic band gap, or the plane wave is reflected, so there's 100% reflection, there's no transmission through the photonic crystal. So this is something we've seen in a previous video. So this is to illustrate a little bit the concept of photonic crystal and photonic band gap. So now what happens if you actually remove some of these nanoparticles? If you remove some of these silicon nanoparticles all along, and you drill this defect line along the photonic crystal, and you send the exact same plane wave. So this is a plane wave with the frequency laying around the photonic band gap. So the light will actually bounce off the photonic crystal itself, but now we propagate through this defect line. So you see it's confined. So you see the electric field is being confined within this defect region. There's no field propagating inside the photonic crystal. You see that the field does not decay as it propagates along the photonic the defect line, and once it's reaching the other side, it acts as a point source emitting those spherical waves. Now you can do more complex patterns with additional channels that's going to serve as waveguides. It propagates through this main line. The electric field is going to reach out the intersection. It's going to split into three fairly equal amount into the branches, and then it's going to emit light on the other side. So something I want to point out here is that first the light can actually bend along tight corners. It splits into three branches fairly equally, so there's the same amount of intensity, the same amount of optical field propagating through each of these three branches. And the third thing I want to mention, and that's the reason why I've designed those two branches with this particular design, is that the electric field reaching out the end of the channel on the upper branch versus the end of the channel at the lower branch are actually out of phase by 180 degrees. And each of them is actually showing here an electric field pointing downward with an electric field pointing upward here. So there's a 180 degree phase shift between the fields that are being emitted here and the fields that are being emitted at the from the lower branch. And both of them were shifted by 90 degrees with respect to the first one. So you see that we are in between two nodes when the fields are reaching out the end of the central channel. So there's a 90 degree shift between the upper and the central channel, and a 90 degree shift between the central channel and the lower channel. So you can see that there's some interference effect that are actually result from this phase shift between the three channels. So now let's focus. Let's go back to a different type of defect, which is the point defect. So if you have, rather than having a line making the defect, we have just removed a few elements that makes a point defect. And instead of having a plane wave, we just used a point dipole, an electric dipole placed in this cavity. So this point dipole emits light, which is with a frequency in the band gap, in the photonic band gap. So let's see what happens to the field once the dipole emits. So you'll see that the field emits light in this photonic band gap, and the fields are actually confined within small region of space. So there's no propagation of light outside of the defect within the photonic crystal. All the fields are confined inside this defect. So you're forming a cavity which is trapping this electric field emitting from the dipole. Now, if you send light the dipole from the dipole placing this cavity, but now the frequency is actually outside of the photonic band gap, just as a comparison, you see that the fields are actually propagating through the photonic crystals from this point source and being emitted outside of the photonic crystals. So this is summarizing a little bit what we've seen. So the waveguiding properties of these photonic crystals when you have defect lines. So you can use the photonic band gap to your advantage to really confine and guide the optical excitations from an optical source through a particular channel, which is composed by these defects. So it could be a straight line, it could contain bends and curves. You can actually split fairly equally. So this is something which is used for circuitry and logic. So we're going to see that in a minute. You can also use those defects for trapping. So this is what we've seen. So we have a photonic crystal with just a point defect, and you just remove a few elements, and then you have light which is just being trapped within this cavity. So you're forming very high quality optical cavities, and we're going to discuss that also in a minute. So what we can do with those defects, as I said, waveguiding and trapping, if you combine them, you can really design very complex systems. So waveguides in photonic crystals really can transport light along tight corners and turns. That's exactly what we've seen. So this is something which is very interesting. There's ideally no loss or very minimal loss, especially for dielectrics. So you can propagate these signals over great distances. There's also a reduced group velocity dispersion, meaning that there's no temporal broadening of the signals. If you send a pulse, the pulse is not distorted when reaching the other side. So you can really design very complex optoelectronic and photonic circuits using those components. And just an example from a work that has been done by a group in Spain, where they design a complete circuit based on photonic crystals. You have basically an input optical field here, or they call the input port, and then basically the design specific functions based on the type of defect they have. So you have some optical resonators, some phase shift or delay lines, got multiplexers, beam splitters, and so on and so forth. So you can realize different type of functions, and then basically from there you can just have output ports where the light will be emitted. So you can actually control whether or not there's light, if you have constructive or destructive interference, and so on and so forth. So those defects, the traps, those point defects, act as resonators. So they are very important for a lot of applications, because if you trap light within a defect, light cannot escape. It's gonna basically bounce back and forth within this point defect. That's what we've seen in the fine difference time domain simulation I've shown you. So the longer the time the photon will remain in the cavity, will remain trapped in the cavity, the narrow the bandwidth. So we have high quality factor. So the quality factor of a cavity, of a resonant cavity, is proportional to the eigenfrequency of this cavity, and the time the light is being trapped in the cavity. So the longer the time, the stronger the resonant factor. Why this is important? Well, same thing. So if you have long times and a small volume, so if you have a long time, you have a high Q factor for the cavity, and if you have a small volume on which this light is being trapped, then you're going to enhance drastically this light matter interaction. So this is, for instance, well illustrated by the Purcell factor we've seen in chapter 4, which depends on the wavelength of light you're actually using and in the medium where you look at, and you have this quality factor for the resonant circuit or the resonant cavity, which is involved in the volume of the cavity. So the smaller the volume and the greater the quality factor, and the more enhancement you're gonna have for this light matter interaction. There's just some key examples of applications of photonic crystals that can be used for light focusing and lensing. So we're gonna rediscuss that in the next slide. So I won't expand on that. Optical fibers have benefited from photonic crystals. So rather than having a very bulky glass optical fiber, you can actually design a very small photonic crystal type of fiber that will confine the light within this line defect. So this is a defect line that runs through the fiber, so light is being confined and does not penetrate within the crystal when the optical field propagating here as a frequency which is laying in the band gap of the photonic crystal. So this is just an image of the confinement of the optical signal within such an optical fiber. So you can drastically decrease the volume of the optical fibers to a very, very small micron scale element. Lasing as well, so those two-dimensional photonic crystals that can be used as Bragg mirrors and form basically lasing cavities, and then basically obtain very, very strong lasing. Biosensors as well, as I mentioned, if we have a long time living photons in a cavity, then you're gonna have very narrow resonances, and that can be used for biosensors. So I just said that lensing can benefit from this. There's been a lot of work where super lensing has been achieved using periodic structures, and that allows basically to go beyond the diffraction limit. So the idea is that if you have an object and you have a photonic crystal or a periodic structure that can be considered as a negative refractive index medium, then you can actually bend light such as the image is sharp. So this is just a computation simulation of a point source through this kind of photonic crystal, which is designed with materials and periodicity and size such as that this behaves as a negative refractive index material, and you can form an image on the other side, which is very, very small. With those techniques, people are able to achieve 2/3 of the diffraction limit. So you're able to beat the diffraction limit we talked about very significantly using those artificial structures. So something which is also very important, I'm going to briefly talk about, is the concept of metamaterials. And we're going to finish up on those metamaterials. So metamaterials are materials that are engineered artificially to have properties that are typically not found in nature. Such properties can include negative refractive index, hyperbolicity, chirality, biaisotropy or bianisotropy. And these are just a few examples of such metamaterials. You see that you have also chiral structures. You have those more complex geometries. So in the end, they are composed of densely packed elements on a periodic array, and they serve as just artificial atoms. So that's why we call that metamaterials, because those elements that are arranged on the periodic array are meta atoms. So the specific subwavelength of this arrangement of these atoms actually results in novel properties that we can engineer. So in the end, you can ask, okay, so then what's the difference from photonic crystals? These are the same things. Well, yes and no. So they are both periodic, they are both designed artificially, but in fact, the photonic crystals are in fact periodic arrangements for which the light is constant, is typically of the order of the wavelength. Because the photonic crystals rely on diffraction for their optical properties. On the other hand, metamaterials, or in our particular case, optical metamaterials, because you can have also acoustic metamaterials for acoustic waves, but in our particular case, we're talking about photonic metamaterials. The arrangement is much smaller than the wavelength. So the separation distance between the elements is much smaller than the wavelength of the electromagnetic excitation which is being used. So the diffraction in that particular case should be avoided. And that's why they can be actually treated as effective medium. And you can actually calculate an effective dielectric permittivity and magnetic permeability for this type of metamaterials. So that concludes this chapter 6. So these are the key points we discussed about the principle of photonic crystals. We saw that they already exist in nature in all 3 dimensions, 1, 2, and 3 dimensions. We discussed about the properties of these photonic crystals, introducing the Floquet-Bloch theorem, discussing about the photonic band gap and the photonic band diagram, their optical properties via the transmission. We talk about defects in photonic crystals for waveguidings with defect lines and trapping with defect points. And we briefly compared photonic crystals with metamaterials